this. So we want to look into a paper titled Prediction of Generalized Anxiety Levels During the COVID-19 Pandemic, a machine learning-based modeling approach. This work was in collaboration with some, the College of Public Health. So one of our members of this also forum. So we are real-life data sets were collected. So we all knew what went wrong during the COVID-19, how people became suicidal. It doesn't just start from that. It starts from having anxiety. When people are very, they suffer a lot of anxiety levels. So can we really identify who is likely going to suffer from this or who is already suffering from this, so that we can offer possible help at the early stage before it goes into a very bad shape? So the aim and objective of that work was one, to classify 2 class and also 3 class anxiety problems early during the COVID-19 pandemic in KSA. So we want, there are two data sets, or the same data set, but with 2 possible predictive solutions. The first one is we want to classify, is this one having anxiety or not? Yes or no, which we call binary classification problem. This is called binary classification problem. See, so it's form of classification, like, you know, we have supervised learning. When we talk of supervised learning, as a way of reminder, is divided into classification and regression. In the classification, so we want to either classify something into yes or no. Is it going to rain or not? Is the student going to pass or not? That is classification, but this is binary classification. But multi-class, sometimes we want to really know, okay, if the student is going to pass, what's going to be the grade of the student? Is he going to get A or B or C or D or E or F? This is multi-class classification problem. It means the classes are multiple. The more the number of classes, the more challenging to solve with high accuracy. But it is possible to solve it. But you know, of course, that is more job. You need to categorize people into multiple classes. So in this work, there's one option of classifying into 2. Is there anxiety or not? And there's the second one, which is 3 classes. So they rank them based, the professional, the medical doctor rank them. There's one, is he available or not available, or there's medium? There's something in between. So these 2 options were investigated in this paper. And then they employ machine learning algorithms to build prediction model. We're going to tell you the choice. As usual, start from the simple to the complex. Now, okay, let's not forget, regression is when you are trying to predict the number. Let's say I want to predict how many people suffer from anxiety. How many? You are talking of number. What is going to be the final exam score for my student? It could be 36.5. It could be 37.5. That is regression problem. Now, so moving further, so we explore the effect of feature selection. See, once you are doing, when you are doing experiment in machine learning, you have to first of all use the original data set. If it works fine, you get excellent result, that's good. But sometimes we need to move further to what we call feature selection. Feature selection is when we try to select the attributes that are better. Sometimes we have many attributes, but not all of them are contributing to the system. You see, it's just like you want to put you try to assist to push a car to work. So many people, some people are even dropping on that car, they are not making it to work. We not say, hey guy, let's just select 6 people that can really be very powerful to do this pushing. You see, we try to identify who are those that are contributing more. So it was, this particular thing was explored. We call it feature selection. We can also have in our previous videos where we're explaining in detail, there are different types of feature selection and why we need feature selection. It was also carried out in this work. So they use it to identify the best features for predicting the 2 class and 3 class anxiety level. Furthermore, see, there are 2 decision tree called D48. Something you can notice from this is that this research was done using Weka. You see, there's a decision tree called J48 inside Weka. So why we use that? Easy for non-computer professionals to understand. Like we are collaborating with medical doctors. We want them to quickly understand what we're doing. So with decision tree, anybody can look at the model built and be able to, oh, this is how it works. That's the advantage of this one. So just like KNRS neighbor, but we use decision tree in this case. And also we use support vector machine because it is robust in many medical applications. Robust in many medical applications. Several successful applications have been built using support vector machine. It's a little bit advanced form of machine learning, but still reasonably, always very powerful, especially when the data is few. So these are the two methods that are used. So when we go to the main paper, I'm going to take us through how you need to make sure that this is very important. It's not just for you to mention to us why you are using a method. It's good to always tell us the justification of why you are using that particular method. Now, then we have the description of the data set. You're going to describe the data set. Tell us what kind of data set you are using, as the case may be. Yeah. So here you can see that it said the data set collection took place during the full lockdown from May 11 to May 26, 2022. So it's a full real-life data set. And then you can see here, these are some of the questions. These are questions from people either on admission or random people on the street. So you can see different questions. You want to know the nationality, the gender, the age, marital status, how many people are in the same house. You see, when you are building a machine learning solution, or you are try to gather data for your machine learning solution, it's very important for you to identify important information. You see, the features you are identifying. You can see here, and remember, knowing how many people are in the house. This is very important, because if you stay alone in those lockdown period, I've seen a lot of people happen to find themselves in this kind of very unfortunate situation. They complain really, really bitterly that they didn't find it easy. If you are alone, no one to socialize with, no one to talk to, and you cannot go out because everywhere is under lockdown. It was challenging for this category of people the more. It was challenging for everybody, but if you are in the midst of people, you can still play at home, maybe your family member, your friend that you are living together, you can play together, you can talk together, you can chat. So that question is targeting that, okay, how many people are in the house? Are you or any of your household members have at increased risk of contracting the coronavirus? They ask some of these questions. I'm going to share the paper with us, so in the forum, so that we can all go through and see some of these questions. So they also ask the qualification, the occupation. So feeling nervous, anxious, or on the edge, worrying too much about different things, trouble relaxing, being so restless, and also several other questions. You see, so based on all these questions, as you can see, are you feeling afraid if something awful might happen? Based on these, these are the target variables. So when you have your data set, you have to identify what are the attributes, the input variable. We call them, these are called the independent variables. Independent variables. These are variables from where we want to predict these are the dependent variables. You have to first of all identify it in your data set. So these are the dependent variables. These are those we want to predict them using this one that we know. Easily, you can easily get this one. You see, the idea about independent variable is you can easily get it from people around, from the data set in the system. However, to get this one, no, you need professional to really judge who is anxious, who is having anxiety or not. So the first, like I told you, there are two predictions in one paper, and sometimes you can have it in your project. Your project is single data, you can have multiple, I call it multi-stage predictive solution. Multi-stage predictive solution. It means you predict the first stage, and then you go to the next stage. Sometimes your first stage might be classification, the next stage might be regression, depending on the kind of problem you want to solve. For example, I'm trying to predict if a patient will die from a disease or not. Then the next stage might be, okay, if you say yes, then can you predict how long it's going to take the patient to live? You see, this is the same project, but now we have multi-stage. First stage classification, second stage classification. But for this case, the two cases, they are classification. So the first type is you want to predict anxiety category, that is anxious or non-anxious. Is this particular sample, is it suffering from anxiety or not? And the second level, the second one is, we are going more now, that is anxiety score categories. Is it mild? Is it moderate? Is it severe? Can you see? It means after you predicted that someone is anxious or non-anxious, this is yes or no, this is binary classification, we also move for that to also show that, okay, what is the level? Is it mild? Is it moderate? Is it severe? This is what we call multi-class problem now, because it has three classes: mild, moderate, and severe. This is the data set. And when you write, you have to describe your data set as much as possible and make it possible for people to reproduce your work. This is one of the conditions that researchers, that editors or reviewers do consider before they accept your paper. They want to see that, okay, can somebody pick up this paper and reproduce what you have done? We come back to that. This is very important. It means you tell us at least some little thing about it. So experimental setup. Experimental setup is very, very important in any work you do in machine learning. You have to tell us this as much as possible information without wasting people's time, by the way. So people used to ask me then, Doctor, how do we know what to say and what not to say? My simple answer then is, anything that if you don't say it here, there's no way people will know about it. It becomes compulsory for you to mention it in your paper on the experimental setup. You see, you don't need to start telling us how to use Weka. Anybody can just ask Mr. Google, how do I use Weka? They can get it easily. No. However, the experiment was carried out using Weka. This is very important. So that that person will know that, okay, this is the environment where we carry out the research. Very important. But in order for you to start, you need to download Weka. Then you need to start. You need to go to, no, you don't need to tell us that. Anybody who wants to do research can find out about that. But if I don't tell them what I've used for my research work, they might not likely know what platform I've used, which is very important. Now, hyperparameter tuning was applied. That is, we carry out hyperparameter tuning. Let them know about this, and you are going to give some details later. When we look at the paper, we see. Recursive feature elimination was applied. That is, in doing our feature selection, we use what we call recursive feature elimination, which is one of the several types of feature selection we described in our earlier videos, so we can check them up. Then another thing that's very important is, how do you partition your data? This is tenfold cross-validation was utilized. Tenfold. There are different types or different ways of evaluating machine learning model. Majorly, they are divided into two, as just a revision for us. We have what we call the hold out method. Hold out method. In the hold out method, you just divide your data into two or three. 70% training and then 30% for testing. Or I use 70% for training, 15% for validation, and 15% for testing. Any of the two is fine. We call them hold out method or direct partition method. And then the second one is called the n-fold cross-validation. We already discussed this also in our previous videos, so we can also check it out. N-fold cross-validation, whereby we partition the data into, but in this case now our n is 10. If your data set is few in number, you can use 5-fold. It means, what do we do here? You partition your data into 10 places, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, with equal partition, averagely. So let's say I'm having 1,000 data. So I try to make sure that 100 is here, 100 is here, 100 is here, 100 is here. For two class problem, I also want to make sure that out of this 100, 50 is class A and 50 is class B. I make sure these are available in all the 10 partitions. Then I start my training. You start by training with all these 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. You combine all these 9 together, which is going to be 900. Use it to train your data and use the last one to test. Next, you combine from 1, 2, 3, 4, 5, 6, 7, 8, and 10. You leave 9 out to be used for testing now. Next time, 7 is going to be used for testing. Next time, 6 will be used for testing. It means for every run, you are going to make different partitions to testing. At the end of the day, you are going to have 10 runs. So 10 results. Then you are going to find the average of these 10 runs. That's going to give you the result for 10-fold cross-validation. So you have to tell people how you partition this data. There was a case of one of my students that reviewed a paper. The paper didn't say the kind of partition they use. I said that paper should be rejected, should be removed from the literature. Because if you don't tell us how you partition your data, how can we repeat your experiment? And we later found out that the paper was published in what we call predictory journals. Journals that don't review paper. They just collect your paper and publish and collect money. This is not good. Every paper being published, it must be possible for people to pick it up and repeat what has been done in that paper. This is very important. And that's what reviewer we call the reproducibility of your work. Can we reproduce your work? If no, that paper will be rejected. If it is a very standard journal. The first check, do you provide enough information for us to be able to reproduce your paper? Even though they might not have time to reproduce it, but if we want to, can we do it? So they will look at your experimental setup. So this is very important. We have to provide the necessary information. So here we use 10-fold cross-validation. So we mentioned that. You are going to mention also the performance measure that you're using, accuracy, precision, and recall, and also of that thing. But very important is how you partition your data. Did you do feature selection, the hyperparameter tuning? Then, because we need to know the final parameter that you use. If you just tell us we use support vector machine, but we don't know the parameter of support vector machine you have used, definitely it's not enough. That kind of paper is substandard. Now, so having said this, so we have the optimization, the optimal parameter, and also other stuffs we are going to see in the main work as we move on. Now you can see this is the optimization for 3-class problem. So during the optimization for 3-class problem, I usually recommend for my working team, it's good to show you optimization of parameter. Let's say this is optimization for support vector machine. You see, for support vector machine, you want to know the value of C that's going to work for you. You see, the parameter, it means you run your data, you keep changing the parameter. You can see here, it started from 1. It started from 1. You can see 2. C is equal to 2. C can take any possible value, even from 0 point something, 0.1, 0.2, but it cannot take negative value. It's one of the very important parameters for support vector machine. So it was optimized. You can see different optimization value. You keep checking. So later I'm going to teach us how we can do a kind of more of the grid search method. You can also set it up in Weka, whereby you can set all the parameters and you can run it at a go. However, I like to start with my team, simple way so that they understand how it works and they can do it by themselves without any complication. Yeah, sometimes when you use software to solve every problem, it make it hidden. How do we do it? Many people don't know it. They just take the code and click, it runs. How is it working? We don't know, no. So I like the student to do some kind of manual optimization themselves. Once they get used to it, then they can automate it and make it faster. But at the beginning, it's good to know how it works one by one. So you can see here, this is 1. We run the experiment for that data. This is for the 3-class problem. There's another one also for the 2-class. So we run it when it is 1. We got this value. This is 93, 90, yeah. We run it again. We run it again. We keep running it. It keeps changing. You can see 99.4. It goes to 99.5. You keep going. You keep changing the value until the value is no more changing. It means it has become, you have come to the maximum possible. So we're going to pick the value that gave us the maximum here, which is like C is equal to 4. It means my optimized regularization factor C is 4. The value is 4. And at that point, we were almost getting 100% or thereabout, which is excellent. Now, which means we know the value of the C. Now, however, in order of importance, the most important parameter, hyperparameter, we differentiate this also before, the difference between parameters and hyperparameter. There are many parameters when you are using Weka or using any software. However, hyperparameter is the one we are interested in. And what is hyperparameter? Hyperparameter is any value that is passed from one function to the other, or from one main program to the subprograms. But hyperparameters, they are those parameter values that will affect the machine learning algorithm, the ML algorithm. See, you can have some parameter like how many iterations. These are not, they don't affect the machine learning algorithm. These are set for convenience. But things that affect the algorithm themselves, we call them hyperparameter. The number one that is most important is the kernel function. Kernel function. So we first of all select kernel function. When you know the value of kernel function, then you go to C. C is the next important one. Now, in the kernel function, we have the polynomial kernel, we have the normalized polynomial kernel, we have the PUK, we have the RBF. These are usually the 4 available in Weka, depending on the data set you are using. Now you can see here, when we try to run the experiment for each of them, run it using polynomial kernel, use the other one, then you will know the one that is better. This is giving us 99 point something. So it means this is the best kernel for us. So we are going to choose it now. We have a table, optimum hyperparameter for the proposed SVM model. So we're going to summarize it in a table, which means kernel is polynomial kernel. C, we have 4 as the best value. You see? And then we have other parameters, but these 2 are the most important parameters in SVM. Then we have the epsilon also with very small value, but sometimes you need to also tune the parameter and get the value that's going to give you the best result. This is what we call optimization. You see, it's very important to do it. If you don't optimize the parameter, the hyperparameter, then you might not be fair to the algorithm. You just declare that an algorithm is not good. Meanwhile, you optimize one, you didn't optimize the second one. This is not correct. In fact, it could be a fraud. We have seen people do this because they want to promote their new system. Somebody just proposed a new machine learning algorithm and you need to sell it to people that it's working. He optimized for his own algorithm, then compare it with neural network without optimizing neural network. This is not allowed. This is a fraud. You see, it's against academic integrity. So we have to optimize the 2 systems to look for what is the best hyperparameter values that will work for this data. Because always remember what I used to tell us, let the data speak. Let the data speak. So let the data talk to us. The data will tell the hyperparameter which value is going to be good for me. Because when we look at the data, we don't understand what is inside the data. So when we slot in the data into the platform we are using, then we provide the algorithm, then the hyperparameter will indicate which value works. So for this project, polynomial kernel was the best identified with regularization factor C of 4 and also the epsilon value. That's for super vector machine. Then for the for the decision tree, one of the unique thing decision tree is it doesn't have much of optimization of hyperparameters. Majorly, you turn the confidence factor, which was checked. You can see here, it started with 0.15. You don't just stop because it's high. Maybe you get another better one. You can see it goes down, it goes down, it goes down, it goes down. Even though this kind of plot is not compulsory, but I usually advise people to put it in their papers. When you're writing paper, you want to communicate someone who is not going to see you to ask you questions physically. It is whatever you put on your paper that will impress him about what you have done. So I usually encourage people to write it, document what you have done. So with this one, it is an evidence for the reviewer that yes, you have actually carried out the hyperparameter. Because I have to mention at this point that unfortunately, some people, they don't do any parameter optimization. They just fake it. He just produced a table here and they say, okay, we did upper parameter optimization. We got this, and they move on. By the time you pick up their paper, and they are going to fake very excellent results. We got 99% accuracy. If somebody is getting 99% accuracy, what else do you need? But by the time you pick up those parameters and then repeat the experiment, you will not be able to get what they claim to have gotten. This is very, very wrong. Again, it's against academic integrity. Whatever we are reporting to the outside world, we have to make sure that it is correct. And that's why once we have done your hyperparameter tuning, if you can present in a small graph like this, put the result in Excel, you can still draw this Excel. At least any reviewer can see the way your parameter values are changing and the corresponding output of your model. Finally, we settle for this one because it gave us the best corresponding highest accuracy. So this is how we do the optimization. For the other two, for the two-class problem also, because this is now another output. It's the same data set, but the outputs are different. One is 2-class, the other one is 3-class. We have to do the optimization again. And you can see that the optimization was a little bit different, the values. Look at this one now. The kernel is still the same, polynomial, which is good, but C became 2 instead of 4. So that's why we have to do the optimization again, because it is considered to be like another data, because the output is different from the previous output. The previous one was 2 classes, while this one is just 2-class problem. We repeated the optimization also, and then we achieve the stable result. So next is we also carried out the feature selection. These are very important procedures that we want to also to take note, because sometimes if the output is already correct, everything is fine, we might not need feature selection, but sometimes you need to do feature selection to reduce the computational complexity. For example, if you look at the number of questions, look at this number of questions, so many questions. There are some other questions that are taken off because question 1 up to 37. Instead of having these 37 questions, can we do feature selection to reduce these questions to like just 5? This is the idea of feature selection. Can we reduce the number of questions we are asking people? So it's going to be easier for us to interview people. So our model will be easy, it can be easily used in clinic, because once you have a lot of medical questions to ask people, people lose interest. So can we do feature selection to actually reduce the number of features? See, this is what feature, sometimes we succeed in using it, in reducing it, and sometimes it doesn't work. Again, it depends on the idea of let the data speak. In some situation, if the questions are interrelated, you might not be able to get them to be reduced considerably well. So that is on feature selection. I think we are going to call it a day at this point. So because of our time, to respect our time, and then if there's any question for what we have covered so far, we are going to take a few questions before we call it a day. So by the grace of God, next week we continue from feature selection, and then we are going to look into the paper itself in detail. How do you write your own paper? What are the constituent parts that you have to pay attention to? Your abstract, your introduction, of course, the description of experiment, empirical studies, and host of other stuff that we are going to pick up once we finish the summary of the paper as presented. Then we're going to look into the actual paper itself and then see how far it can go. Now, so as we thank you for listening. So we are going to take a few questions as we said. Thank you.